So it's kind of a probabilistic take on the security thing. But if we would leak the pointer somewhere, or if we would have a bug, or if the malware is lucky, it could find out the location of our code cache, overwrite instructions, and do evil things. I mean, actually, we don't really want to rely on that probabilistic form of security. So we implemented an mprotect-based form, which write protects all internal data structures of the binary translator. And as I said before, we have two different levels of execution. One of the levels is the privileged binary translation level, where we lift this mprotect restriction on the internal data structures. And when we branch back into the translated user code, we kind of lock down all our data structures and then let the execution continue. And as the execution is not allowed to execute any unchecked system calls, we can kind of make sure that this protection is only lifted by the binary translator itself, and thereby protecting all our data structures and forming two different forms of two privilege levels in user space. The trade-off of that approach are the additional mprotect system calls, which incur a higher overhead. But, well, it kind of pays off in the end, because you are sure that the user space program cannot override your data structures instead of just the probabilistic guarantees. Another security extension is to check return instruction pointers. Whenever we execute an optimization for function returns, we can check and validate return instruction pointers so that they point right after a return instructions, they point into the same module, and that they were not changed by any other things or some buffer overflow or whatever. We can kind of also have a shadow stack hidden from the user and validate that the instruction pointer stays the same. When we translate and indirect control flow transfers, we can also validate the targets of these control flow transfers and ensure that only already translated, that they branch to an already translated start of a basic block. This is done for both indirect calls, for example, function pointers, return addresses, and indirect jumps as well. Indirect calls and indirect jumps. If the target is not valid code, not in a code region, or some other illegal things, like a jump into a different library, we can terminate and kill the program and say, well, this program does bad things, we have to stop that. So now we've got the user space virtualization, we've got the binary translator, we've got some security hardenings, but the program is still allowed to execute any system call. So we have to add a system call interposition framework where we intercept all system calls that the program does and all interactions with the kernel. So the system call interposition framework that we propose guards or rewrites all system calls that go through the sysenter and the interrupt machine code and redirect these to a validation function. Depending on the system call and the parameters and the arguments, the system call validation function decides to allow and execute the system call, disallow the system call and terminate the program, or it decides to redirect to some user space function that is implemented in the privilege level of the binary translation function. So we can make the program believe that it is executing a system call, but in fact it's just staying in user space and executing some functions that we provide. These validation and checker functions are based on a per system call basis. So to redirect these system calls, we have a big table which defines functions for each system call, and we can override these function pointers and redirect these to our user space function. So one example for that would be to intercept the getGID command that is well, we intercept the getGID command and implement it in user space and just do some stuff that, yeah, that makes it a little bit more interesting. So whenever the program executes a getGID, getUID, or any ID function, we disallow the system call, but redirect it to our user space function and return ID of 0, which will tell the program that we are root. So let's have a short look how that works. If we run the ID program like that, oh, let me make that big. No. Then it looks like that. So the ID program is executed. We have a UID of 1,000, a GID of 1,000, and some groups. But if we use LD preload of the BT library and redirect to that implemented function of getID and execute ID again, we see suddenly we have an ID of root, a GID of root, and our other groups as earlier before. So we see that this can be used for many different things. You can also play with the binary translator to instrument some functions and to instrument some code, and you can also use it for debugging. And this is a nice tool when you do some reverse engineering or some experimentation with some code that you have. So now that we have the system call interposition framework, we can define which system calls are allowed and are disallowed, and we can define an explicit set of calls that are allowed. So to make my point that it is really usable, I'll show some performance numbers. We use the spec CPU 2006 benchmarks. These are some scientific benchmarks to measure program performance. And we use 3 different configurations: overhead of binary translation alone, binary translation and system call authorization overhead, and the additional mprotect security. And yeah, the overhead looks a little bit like this. On average, if we only use binary translation, we have about 7% overhead. If we add the security validation and system call validation, we have 7.4% overhead on average. And if we add the memory protection, we have 9.5% overhead. This overhead is low and tolerable for security if you want to use it. Mind that only a selection of benchmark is shown of interesting numbers. There's the first number is the Perl benchmark with an overhead of like nearly 70%, which is really high. But this is mainly because at that stage we kind of didn't have one additional optimization implemented. And this kind of makes clear that the optimizations that we have for the binary translator are important. And yeah, if you just miss one case, or the prediction is wrong for one case, you kind of run off into a very high overhead. So it is really important to fit the optimizations to the correct locations. So what is more important for you will be what kind of protection does secuBT offer? Well, secuBT offers protection against heap and stack-based overflow. As soon as the evil code is to be executed, we kind of see that. We see malicious code which is not really, which doesn't really belong to the program, and we can then kill the program. What is important as well, that we also protect against return to libc attacks. If you deny the correct system calls, you can already see while this program is executing some unintended system calls that it has never executed before, so we'll just kill it. And also overwriting return instruction pointers. If we have the shadow stack, we can just recognize that and kill the program. So it has a very broad application, offers many different protection mechanisms, which can, some of them can kind of be implemented in a on the source level.